In my previous videos, I often mention the Fourier plane of the condenser, or the Fourier plane of the objective, and Fourier filtration effects, etc. Clearly, all this Fourier stuff is quite important for understanding how a microscope works. In this first video, I'll go over the basics of what Fourier analysis is and introduce you to some important concepts, but I won't stop there. This series is aimed at giving you a detailed practical knowledge of Fourier analysis, so I'll also cover the maths in a practical way in both this and subsequent videos. Jean-Baptiste Joseph Fourier was a French mathematician who lived in the time of Napoleon, and he was also a governor, diplomat, and local administrator over various populations and districts. He had a fascination with heat, and with the way it was conducted by various materials, and he used math to model this. He was interested not just in heat travelling through metal rods, but the temperature of the Earth, its conduction below the Earth's surface, and the setting up of the climate at different regions, and even the temperature of interstellar space. So Fourier was actually a pioneer of climate science. By making experimental measurements on how temperature changed through sample materials, he found that these temperature plots did not follow a pattern that could easily be described by simple equations. However, Fourier was aware of the branch of mathematics we call harmonic analysis, which allows repeating, that is periodic, functions with complicated shapes to be synthesized by summing up series of pure sinusoidal waves of different frequencies, phase shifts, and amplitudes. These pure sinusoidal wave components are called the harmonics of the function that they produce when added up. So, Fourier did not invent this concept, but rather he developed harmonic analysis into a general form, so it could be used to model almost any arbitrary recorded data and not just continuous periodic patterns. Let me show you a real-life example for a two-dimensional function. For this experiment, I'll be using this simple LED backlight with a variable brightness control to help us see through all the harmonics I'll be stacking up on top of each other. Instead of summing up sinusoid images on a computer, I'll be using actual sinusoid harmonics printed onto transparent plastic like this. As you can see, this has some printing defects, and the printer uses only black toner, so it has to use dithering to try and create smoothly varying optical densities. So the result will not be perfect, but I thought it would be better to show you this in real life, so to speak, so you can see that all this math that might seem quite abstract to some actually describes real-world events. So, using Fourier's methods, I was able to calculate what set of pure sinusoidal wave patterns, or harmonics, I needed to print out onto this transparent plastic, such that when I add them all up on top of each other, I get this general non-periodic pattern of a capital letter A. Notice that some of the harmonics have higher contrast in their wave patterns than others. This means that those harmonics have a greater amplitude as is required to fit to the desired end-goal function. In the language of Fourier analysis, we describe the amplitude of a harmonic by the magnitude of the Fourier coefficient, but I'll explain that terminology to you in more detail later. Also note that all these sinusoids are shifted to a specific degree. They aren't all symmetrically positioned or starting from the same point in the wave, like a pure sine or a pure cosine. This shift is described by the phase value of the Fourier coefficient. Again, don't worry if that's not totally clear right now, I'll explain it again in more detail later. For now, just understand that it's not the frequencies of the harmonics on their own, but the specific combination of amplitude and phase shift for each harmonic that uniquely makes them add up to the desired end-goal shape. By using a set of waves of these same frequencies, and by simply varying the relative amplitude and phase shift of each one of them, I could make them add up to any letter of the alphabet or any arbitrary shape I want. Here you can see the end result of summing up all these specific harmonics. Although not a perfect letter A, it's close enough, and the imperfections are due to the limitations of my printer, not the mathematics. It was Fourier who gave us the notion that any arbitrary plot, like my letter A in the practical demo, can be considered to be a function, and he also showed how these arbitrary functions can be exactly equaled, not just approximately so, by the addition of a suitable number, including possibly an infinite number, of harmonics. His method of analyzing a general function to calculate its component harmonics is called Fourier analysis of the function and uses the forward Fourier transform. Adding up all those harmonics to reproduce the original function is called Fourier synthesis of the function and is done using the inverse Fourier transform. So, now we know how to describe any arbitrary plot as a summation of weighted and phase-shifted pure sinusoids. So what? Well, as is often the case, if you can describe a complicated thing in terms of simpler components, it becomes easier to apply certain mathematical operations on that complicated thing by applying those operations on the simple components instead. Any operation done on the components of the Fourier transform of a function is referred to as an operation done in the Fourier domain or frequency domain, as opposed to performing operations on the untransformed function, which is referred to as performing operations in the spatial domain or time domain, depending on whether your original function was describing some property that varied over space or over time. In these videos, I'll be discussing the Fourier transform as applied to images, so I'll stick to talking about the spatial domain. For example, you've seen from my video on convolution that to perform a convolution in the spatial domain by the traditional roving kernel method, you need to do a ton of repetitive shifts and multiplications and additions over and over and over again at every single pixel position in the entire image. And this can get very slow for large images with large PSFs. If we convolve this image with this blurring PSF, we get a blurred version of the image. No surprise there. But now look what happens when I convolve this pure sinusoid with the same blurring PSF. You see, pure sinusoids have a special mathematical property, in that blurring them merely reduces their contrast without altering their shape. So, the result of this convolution is just exactly the same sinusoid in terms of frequency and phase, but the amplitude is uniformly reduced across the image. This means that instead of doing all those gazillions of shifts, multiplications and additions for every single pixel all over the image to get the convolution, we could have just multiplied each pixel in the image by a single constant instead to get the same result. But it's even better than that. I'll show later that each such pure sinusoid is defined by just a single complex number in the Fourier domain. So this whole convolution process just boils down to a single complex multiplication operation in the frequency domain. Not one multiplication per pixel in the sinusoid, no, just one single multiplication operation for the whole image will give us the same result as the full convolution process, but only because this image has the special property of being a single pure sinusoid. If we convolve this image with this sharpening PSF, we get a sharpened version of the image. No surprise there. But again, if we convolve a pure sinusoid by the same PSF, we just get the same sinusoid, only this time the amplitude is increased. So again, we could have got this same result with just a single multiplication operation in the Fourier domain. No need for all that spatial domain convolution hard work stuff. This is in fact a general phenomenon. Although I won't derive the full maths here, it turns out that if we Fourier transform an image and a PSF, we can get the Fourier transform of the convolution between them by simple one-to-one multiplication between each pixel in the Fourier transform of the image and the corresponding pixel in the Fourier transform of the PSF, because each pixel or point in the Fourier transform represents a single sinusoid harmonic wave. So you can do the exact same operation as convolution between any image and any PSF, but with many fewer sums compared to doing this in the spatial domain with the roving kernel algorithm. To see our convolved image, we then take the inverse Fourier transform of the result of this multiplication to get back to the spatial domain. In simple formula form, you can express this process as shown here. This particular relationship between the Fourier transform and convolution is called the convolution theorem, and it has hugely important practical and theoretical applications in image processing, maths, and optics. Now, yes, you do need to do 2 Fourier transforms forward and 1 Fourier transform back in addition to the one-to-one multiplications, but the fast Fourier transform, or FFT, algorithm makes this a very quick and practical thing to do, so convolutions can be done in a fraction of the time it would take to do it all in the spatial domain. Some practical applications of the Fourier transform include image and signal compression, pattern recognition, spectroscopy, and lots more. Also, it turns out that the Fourier transform is a good mathematical model to describe the way an image is formed by the waves of EM radiation. This has practical applications in forming medical images like MRI or radioastronomy images, as well as explaining and manipulating image formation in microscopes. Something I'll come back to after I've explained the Fourier transform in more detail. In this video, I'll be discussing a version of the Fourier transform that deals with functions that consist in a finite set of numbers that are only defined on a fixed number of points across space, rather than functions that are continuous. Such a finite set of numbers are called a discrete signal or a discrete function. In practice, a discrete function might be the gray level values sampled by a camera sensor at a finite set of regular spaced positions in space corresponding to pixels in the recorded image. In one dimension, such a discrete function can be represented as an array of numbers like this, where we have n samples labeled 0 to n-1, and the value of the function at each sample is just a number. The Fourier transform is designed, however, to handle pairs of numbers at each sample position. This is something that other basic introductions don't tell you, so I want to repeat that point. The Fourier transform actually transforms coordinate points from one domain to the other. It takes in a list of pairs of numbers and outputs a list of pairs of numbers. So, to be precise, it's better to depict our discrete signal samples like this, as if each sample represents a coordinate point with 2 values associated with it. In mathematical terminology, each pair is called a complex number. In this case, the word complex is used in the sense of meaning being composed of more than one component, rather than in the sense of being complicated. The first component of a complex number is called the real part, and the second component, which are all 0 in this example, is called the imaginary part. Mathematically speaking, each such pair of numbers can represent a single coordinate point on a plane, but they're not the coordinate points on the simple real Cartesian plane where both axes are composed of the real number line. Instead, a complex number represents a point on the so-called complex plane, where one axis is the real number line, and the other axis is the imaginary number line. For the simple real Cartesian plane, the members of a coordinate point are often just written as 2 numbers, like this. However, these numbers are actually multipliers or coefficients of some units. So, if we were to express this coordinate point fully, we would instead write 5x, 7y, where x means a unit vector pointing along the positive x direction, and y means a unit vector pointing along the positive y direction. However, by convention, we usually don't write in the x and y. We just all agree to take it for granted that that's what the 2 numbers refer to. So we just write 5, 7 as a kind of mathematical shorthand. The complex numbers are also like this, because they too represent coordinate points, but on the complex plane. If we were to write a complex number out in full, we would write something like this: 5r, 7i, where r is the unit vector travelling 1 unit along the positive real axis direction, and I is the unit vector that describes travelling 1 unit along the positive imaginary axis direction. It's tradition that when you write down a complex number, you omit the r. So this would actually be written like this: 5, 7i, or this, 5 plus 7i. The reason we keep the I in there is because it acts as a signpost to tell us we're dealing with a complex number, because combining 2 complex numbers requires slightly different rules of arithmetic compared to combining 2 real Cartesian coordinates. The difference in the rules is due specifically to the way the 2 imaginary numbers combine. Now, I assume my audience is familiar from school days with the concept of I being defined as the square root of -1, and that any real number multiplied by I is defined as being an imaginary number. So I'm not going to go into a long speech about how this is a terrible naming convention because all numbers are actually imaginary, but that doesn't mean they don't exist, etc. You can read a summary of this on the screen, and if you are confused by this terminology, there are plenty of good videos on YouTube to explain it all. So you might want to see some of those first before watching the rest of this video. So, of course, we can't calculate or write down the numerical result of this square root on its own, but in practice we never actually need to. We only write down the letter I to represent it. The coefficient of I in an imaginary number, like the 5 in 5i, is what we actually use in all calculations involving imaginary numbers. But the I part just tells us to follow certain rules when doing arithmetic on imaginary numbers, or the imaginary components of complex numbers. In this sense, I is just another mathematical operator, so we have plus, minus, multiply, divide, and I. But I is like a modifier for the other operators rather than a pure operator in itself. So, to remind you, these are the rules for combining imaginary numbers. 1. Whenever you multiply two imaginary numbers, you perform the multiplication of the coefficients as normal, but you just multiply the result by -1 and drop the i's, so the result is no longer an imaginary number. 2. You can multiply or divide an imaginary number by a real number. The result will always be an imaginary number. Obviously, if you divide one imaginary number by another imaginary number, the i's top and bottom will cancel to leave a real number as the result. 3. You can't merge an imaginary number with a real number using addition or subtraction. You must keep them separate. This is exactly the same as when adding Cartesian coordinate numbers. It has no meaning to add the x value to the y value because they describe different independent quantities. Mathematicians call this type of independence orthogonality. It implies that a change in the amount of one of those values does not in any way necessitate a change in the amount of the other value. So, when combining two complex numbers as opposed to just two pure imaginary numbers, here are the basic rules. For addition or subtraction, you simply deal with the real and imaginary components separately, as shown in the example. With multiplication or division, there's a bit more to it, because when you expand the terms, you'll be multiplying real components with imaginary components, so forming new imaginary components, and you'll be multiplying imaginary components with imaginary components, so forming new real components. So you have to keep track of the individual sums. Then, at the end, gather all the real components into a single real value, and all the imaginary components into a single imaginary number, and that's your answer. Apart from always following these simple rules of combination, there's nothing special or complicated about complex numbers. Now, getting back to our discrete signal of measured values, this is where the mathematical naming conventions of real versus imaginary become extremely bad. Because all the imaginary components are 0 in this signal, it's called a real signal. If we had a signal where all the real components were 0, but at least some of the imaginary components were non-zero, that is called an imaginary signal. If we had a signal where any of the imaginary components were non-zero, in addition to any of the real components also being non-zero, then this is called a complex signal. Complex signals can be recorded in practice in the real world. For example, consider an electromagnetic wave coming from a source. It might be a much more complicated waveform than is shown in this figure. If you can record or calculate a value for the electric field strength of an EM wave at various points in time, you can record those values as the real component of a recorded signal. Now, if you can record or calculate the magnetic field strength of the same waveform at the same points in time, you can record those measured results as the corresponding imaginary components of your recorded sampled function. The paired values so recorded will behave in the physical world according to the mathematical rules described by complex numbers. So, complex signals and imaginary numbers can be used to describe real-world physical phenomena, further emphasizing that there is nothing non-existent about them. It would be much less confusing to call these something like upright signals, these lateral signals, and these compound signals. But no, the current naming conventions of mathematics force us to use the terms real, imaginary, and complex instead. Finally, you can regard all signals as complex signals. It's just that real signals are complex signals with all the imaginary values set to 0, and imaginary signals are complex signals with all the real components set to 0. So pure real and pure imaginary signals are just special cases of complex signals. The Fourier transform takes as input a complex signal. When the signal is a discretely sampled signal like this, then we use a version of the Fourier transform designed for discrete signals called the discrete Fourier transform, or DFT, which uses simple discrete summations instead of the integral calculus used for continuous signal Fourier transforms. So, the input to the DFT is a sequence of pairs of numbers, where each pair of numbers might represent some value of a thing at some point in space or time, that point in space being represented by the variable k here. However, as I'll discuss in more detail in another video, the output of a DFT is also a set of complex numbers. So, the input to a DFT might alternatively be the output values from a previous Fourier transform. But I'll say more about that in another video. Don't be alarmed by the complicated appearance of these equations. They're not as difficult as they might look. I'll attempt to show you that all these symbols just boil down to some simple arithmetic that you can do on a piece of paper. In fact, I have actually implemented a fully calculated DFT in just a simple Office spreadsheet. This implements a DFT on an input signal with 5 samples. Okay, it's a tiny input signal, but it illustrates just how simple, easy, and practical are these Fourier equations. So first, this is the forward DFT, which decomposes an input signal into its harmonics. And this is the inverse DFT, which sums up those harmonics to reproduce the signal. The key to understanding what all these symbols inside the summation terms mean is to realize that these exponential power terms are not meant to be calculated literally, by taking e, the exponential constant, and multiplying it by itself this many times. No. This is just a mathematical shorthand way of writing an ordinary sine and cosine function using a famous equation called Euler's formula, shown here. If we rewrite the forward Fourier equation by substituting the complex exponential part with its sine and cosine form via Euler, we get these equations, which make it a lot clearer to non-maths experts what calculations are actually being represented here. Remember that the input function, the gk, is a list of n complex numbers, so each number in this function has 2 components, real and imaginary. Because we're going to manipulate this formula a bit, first let's simplify the notation by substituting the big sine and cosine terms for just this capital C and S notation. We'll put the full sine and cosine terms back in later. So now we have this simplified notation, and we know that the gk are all complex numbers. So let's write the gk components out in full, like this. Now you see that we're multiplying one complex number with another complex number. So let's expand this according to the rules of complex arithmetic I showed you earlier. And, eventually, once we gather the real and imaginary terms, we get this. So we have the real component here and the imaginary component here. It is clear, therefore, that the output of this forward DFT is a set of complex numbers, just as the input had been a set of complex numbers. Likewise, for the inverse Fourier transform, we can do the same. So we get this for the inverse Fourier transform. Now, regarding the forward transform, the complex numbers that are output by it which we call Fourier coefficients, define the harmonic waves that make up the input signal. Exactly how these Fourier coefficients define harmonic waves is something I'll be explaining in more detail in another video, but for now I want to explain how the DFT, both forward and inverse, represent sine and cosine waveforms in general by explaining the meaning of this term that we see inside the sine and cos function brackets of both the forward and inverse DFT formulae. To keep the explanation as simple as possible, I'll use the first sine term of the imaginary Fourier coefficient in the forward DFT shown here as an example. The meaning will be the same for all the other times it's used in the rest of the formulae, so there's no need to clutter up the screen. Essentially, this term defines a sinusoidal waveform that is, in total, n points long. This 2π bit means whole cycle, because one whole cycle of either a sine or cosine wave will be generated over an angle sweep of 0 to 2π, as illustrated in this animation. The frequency f determines the number of those whole cycles contained in the entire n data point long waveform. So the value of f in the example sine waveform shown on the right are f equals 1, f equals 2, and f equals 3. This k over n term specifies the position in the waveform. It goes from the start of the waveform, where k is 0, to just before the end of the waveform, when k is n-1. The reason we stop at n-1 and not n is that the waveform repeats itself after n points, and since we started counting k at 0, the nth data point is reached at position k equals n-1. Note that there is no way this expression can specify a value of the sine wave at any intermediate position between those integer discrete k positions. The smooth pale pink lines in the figure are only there to show you what the underlying sine function looks like. So the waveforms used by the DFT, whether in the forward DFT analysis or the inverse DFT synthesis, are all discretely sampled sine and cosine waves, and the values of those waveforms are only calculated at the same n sample positions where the values of the original discrete input function are known. So, now you understand how the DFT formulae represent sines and cosines, let's return to the full forward DFT formulae. Before I explain this in more detail, note that in the special case where all the imaginary components of an input signal are 0, so the input function is strictly real, the forward DFT formulae can be simplified to just this. Now, the value of the Fourier coefficients represent the strength and phase of any particular harmonic waveform in the signal. I'll explain how they capture the phase information in another video. But looking at these equations, you can see that the way the forward DFT calculates the strength of a particular frequency waveform in a signal is to simply multiply the input signal with a pure unit sine and cosine function which have that frequency. The multiplication is done point by point at each of the sampling positions for both the input function value and the waveform value at those corresponding points. Then, the results of all those multiplications are summed up across the whole range of the input function into a single number, which is the Fourier coefficient value. Effectively, this is like a correlation operation. The more similarity the input signal has to a particular frequency sine or cosine, the greater will the result value of this operation be. The sign of that result value will be positive if the correlation is positive, that is, if the GK values rise as the waveform rises and falls as the waveform falls. Or that value will be negative if the correlation is negative, that is, if the GK tend to rise as the waveform falls and vice versa. So this also explains why, even if all the input signal values are positive, you can get some negative values in the Fourier coefficients using these equations. Remember, these summation equations operate over the whole range of k, the spatial dimension, but for only one frequency waveform of frequency f, to give you the value of the Fourier coefficients for that frequency only. To get the whole set of Fourier coefficients, you need to repeat this operation for each frequency in the full range of frequencies that the signal could possibly contain, which I've represented here as being from minus fmax to plus fmax. For the inverse DFT, it's the other way around. We sum up the harmonics over the full range of frequencies, and we do this summation at each spatial data point k of the signal, to recreate the value of the signal at each point k. Just as with the forward transform, for this inverse transform we only use the value of each harmonic wave at discrete points along the wave and on the same sampling interval as the discrete function we're trying to recreate. In this video, I explained in general terms what the Fourier transform is, the type of data it operates on, and I explained in some detail the equations of the discrete Fourier transform. But how exactly do we define frequency in these equations, and how can we know what are the minimum and maximum frequencies that could possibly exist in any general discrete signal without resorting to trial and error? Also, what exactly is a negative frequency? The answers to these questions are what I'll be tackling in the next Fourier video. If you like this video, please hit the thumbs up like button and view some of the other videos on my channel. If you'd like to support the project, you can do that by subscribing to this channel and telling others about it. If you'd like to help me continue this work, take a look at my Patreon page, where you'll find additional content and early bird access to future videos. Thanks for watching.